Good morning, everyone there in New York. This is Matt Taylor. I work on the Rosetta mission. I'm here in Noordwijk, which is a town on the coast of the Netherlands, which is one of the key sites for the European Space Agency. I'm going to give you a little overview of what Rosetta is, the mission that we have, and I'm going to challenge myself here to see if I can share my screen and see if this goes all according to plan. It did before. Let's hopefully get this to work. Okay, so hopefully you should start seeing my screen. I'm not sure if you can or not. Can you hear me at all?
You're frozen now.
Best laid plans and all that, you see. That's what it is.
Yeah. You didn't have any of these issues with the Rosetta signals.
No, no, not at all, not at all. You can still hear me though. That's the main thing. Right, I'm going to try one more time. It's obviously the sharing screen which is starting to cause problems. I've stopped sharing and now it's. Well, you know, I'll tell you what. You can hear me. You can see my horrible furry face on the screen as well, which is frozen, I guess. Um, I did want to show you a few slides, but I'll basically go over them by voice instead. The key thing about Rosetta is, for me, it's an international mission. Although it's run by a European Space Agency, we're collaborating with a number of countries. We're collaborating with NASA. We have colleagues actually that work on the New Horizons mission. Alan Stern, who's in charge of the New Horizons mission, is actually working on Rosetta as well. And so it's something for the world, I would say. So it's something we've all put together. Now, the mission itself, or the spacecraft itself, is around 32 meters across. Hang on, I'm just being told what to do. I'm just going to try. Has that worked at all? Doesn't seem so. Anyway, it's yeah, the spacecraft itself is about 32 meters tip to tip, wingtip to wingtip. So you know, it filled the length of a basketball court. It's weighed about 3,000 kilos on launch. Most of that, or I'd say over 50% of that, was fuel to get to where we needed to go, which was to a comet, Churyumov-Gerasimenko. I'll call it 67P. 67P is a designated to say it's the 67th periodic comet. We needed to go to a periodic comet because you can kind of predict where they'll be, and that's important for deep space missions. Even though we had all that fuel, it took us 10 years to get to the comet. We had to do a number of slingshots around planets. We went past the Earth a couple of a couple of three times, and then past Mars as well to borrow some energy to fling us out towards that towards the orbit of the comet, which goes out to the orbit of around Jupiter. Why do we look at comets? Well, comets have fascinated mankind for years, well, decades, millennia. We look at them because we consider them to be the leftovers at the beginning of the solar system. They were the kind of ingredients. It's a bit like when you're baking a cake and you always have detritus on the countertop after you've formed your cake. There's bits left over. We look at them, the leftover ingredients of the solar system, to get an idea of what the stuff was that was around right at the beginning. Comets in particular are interesting because that stuff that was in them was deep frozen. So when they come back towards the sun, they start to chuck all of this stuff back out again. So we sent our probe all the way to 67P. It took 10 years. Last year we got so far away from the sun that we had to switch the spacecraft off and put it into hibernation for 2 years. So everything was ramping up early last year in 2014. We came out of hibernation, which was a great relief to a number of people, including the guy that wrote the software to get it out of hibernation. And we then started to go towards the target, Churyumov-Gerasimenko, as I mentioned before. Bear in mind that we only considered what this comet looked like from Hubble-based images and ground-based telescope images. We had a rough idea of what it looked like. We didn't know specifically what it looked like, and that's what we learned very soon after coming out of hibernation. So in spring last year, we suddenly saw this duck-shaped object in front of us, and that gave us some challenges to try and decide how to land Philae, the lander of the Rosetta mission, on the comet itself. And that gave us a very constrained set of observations and time to try and decide where to put it on the comet. Most other missions take years to decide where they're going to land. We had 3 months, and that was on an object that we didn't actually know what it was looked like and what the gravity around the object was like. Just out of interest. Oh, have you got the slideshow up now?
Yes.
Well, I think I'll have. I don't know where I am now in terms of slides. I think it's probably easier to just for me to talk over. If
Well,
you put
you can keep showing them while you're speaking.
I'll tell you what. Put on. Let's go with the fifth slide. That's the slide that shows the comet. Hopefully, so the thing that looks like something out of Star Trek, which gets the conspiracy theorists going. So that's the object we found, and we had to try and decide where to land on that. If you go to the next slide, we show when we had approached it in October time. We have this wonderful selfie, which are quite popular in space now, where we show you can see the solar panels of Rosetta and the comet in the background. If we consider, I've referred to this comet many times as duck-shaped. It has this head and a body. And when selfies are taken, apparently you sometimes get duck faces, and for once you can actually say in space that this one has got a duck face, if you could refer to the comet as a duck. Now, if we go to the next slide, this is a little cartoon. The problem here is I'll not know how it's running. These have been a fascinating vehicle to demonstrate the science that we're doing and what the mission is. These cartoons are created in English and a number of other languages, and they're a fantastic vehicle for teaching children about the mission and about the science we're doing. We went out to about 20 or so kilometers, and then we pushed the Philae lander off, and from 23 kilometers we got to within about 120 meters of where we decided to land. Now, there was a little bit of a problem in that the harpoons that were originally designed to affix us to the surface didn't work, and that meant that the lander itself had to scoot across the surface of the comet, clipping it a couple of times, and eventually landing about one or so kilometers away from our original landing spot. Now, I'm a glasses half full person. I consider this was lucky in a way, because we found subsequently, both from the landing itself, the initial one, and also some measurements we took with a hammer on board the spacecraft or the lander, that the subsurface just below the dust layer was very, very hard. So perhaps the harpoons wouldn't have actually got us in there, and that would have pushed us away from the comet forever. If we go to the next slide. Hopefully the animation is finished. I show an image taken from the camera on board the lander on the left-hand side, where we see this fantastic environment that we've landed. And there's a nice juxtaposition here where you have the foot of the lander, which is about 20 or so years old, and then we're contrasting with something that is billions of years old. This is stuff that the entire solar system was made out of underneath us. And from these images that we had on the lander, there were about 9 cameras on the lander. We put together a local landscape, and that's what's shown on the right-hand side here of how we think things are. Now, Philae carried out its science, and if we go to the next slide, eventually its batteries ran out as designed. After about 60 or so hours, and it went into hibernation. This is what it was supposed to do, and then recharge its batteries. Because it was in this strange place, it was going to take longer to recharge its batteries and go into do some more science. All along this time, the Rosetta orbiter itself has been doing lots of science. If we go to the next slide, here we show some another graphic. I like these graphics. This is basically showing some of the gas that's coming off. We have it's not a very nice environment. It's a very dusty environment. It also smells quite a bit. We have methane, alcohol, some stuff that smells, well, there's basically ammonia in there as well. So maybe after your dinner, and if you all go out to the bar, it's going to smell a bit like that as well. So it's an interesting and rather unpleasant perfume that the comet gives off. But these are all the building blocks of the solar system. We also can pick out bits of dust that are floating around the comet, and we look at those. We investigate those individually. We name them. In fact, I think we had one called Boris that we have an ion gun on board that we look at the spectral reflectance of these dust particles, and we show that he was made of magnesium and sodium once we'd shot him with an ion gun, which again is important in constraining how the comet and what the comet is made of. Go to the next slide. One of the major problems we've had is how dusty the environment is. We went down to about 6 kilometers with the spacecraft, did a flyby right on with the sun behind us, and that gave us, if we go to the next slide, this wonderful image, which is 225 meters across. We see this dark patch on the right-hand side. That's actually the shadow of the spacecraft on the surface of the comet. There are subsequent frames where you see this shadow moving. This is a very important measurement. because it gives us an idea of how the sun is reflecting off the surface of the comet. It's also lucky that we got this, because there was an onboard issue about 10 or so minutes after this, that if that had happened earlier, we wouldn't have got these vital measurements. We go to the next slide. I show about 3 months worth of views of the comet. We can see lots of dust coming off. This is the coma, the outer atmosphere of the comet, blowing out into space. These things from the ground, we can see, well, we can see Churyumov, Gerasimenko using telescopes, but other comets, they'll stretch this tail on this coma can go out to hundreds of thousands of kilometers. It's a very dusty and dirty environment. So if we go to the next slide, that's basically the challenge we have. Around June time, we actually heard from the lander again. It had come back to life. But the problem was we weren't close enough to get a secure signal, and that's where we were left, actually. After a month of having contacts, the lander telling us that it was fine, we had to go further away as we were approaching perihelion, the closest approach to the sun where the comet gets the most active. And so we got further away, and we haven't heard anything from the lander since then. The next slide gives you an indication of some of the vistas that we can see as we fly across and around the comet. This shows down into the neck region of the comet. We go to the next slide, you see these two shots, one just showing the diverse terrain, the dusty terrain that we were examining all the time. We see on the left-hand side, actually, we see a nice plain in the middle, some dusty plains with some boulders, some block-like objects, and these have been named after the Giza necropolis in Egypt, and one of the biggest ones there is about 40 meters or so across. We've named that Cheops after the Grand Pyramid of Giza. Now to the penultimate slide, so you know how long I've got now. We show a movie, hopefully, of the comet on the day that it was closest to the sun, where we saw a lot of activity. There were lots of outbursts of material coming off. At this time, we're looking at about 1,000 kilograms of material coming off a second. Now, the activity of the comet is starting to die down. We're getting closer to the comet as well, because the dust environment is getting a bit less intense. We are listening for the lander again. We're still doing our science. And just going to the last slide now, this is where we are now. We've gone past the sun, the closest approach to the sun. We are drifting off away from the sun again. We are running until September next year, and at that point we will carry out a controlled landing, or controlled impact, I should say. I think that's the technical term, to bring the Rosetta orbiter onto the surface of the comet as well. And all I ask you to do is stay tuned to the ESA Rosetta Twitter feed, the ESA Rosetta blog, where all of this good stuff is happening. We're having science conferences all the time, showing how great the science is when we all work together. Thank you very much for your attention, and sorry about the technical problems.
Thank you so much.